Welcome back to the course on linear algebra for data science. Today we are going to learn about subspaces. First of all, let us see what a subspace is. A subspace of a vector space is actually a subset of the vector space, which itself is a vector space under the induced operations of vector addition and scalar multiplication. Or mathematically we can say, let S be a non-empty subset of a vector space V with operations plus and dot. S is a subspace of V if and only if the following two closure conditions hold. First closure condition is closure under addition. That is, suppose we have two elements U and V in S, then their sum must also be an element of S. The sum must not be an element of only V. Okay, so if we take two elements of S, their sum must be in S. And the second condition is closure under scalar multiplication. That is, if U belongs to S and alpha is any scalar, then alpha dot U belongs to S. So these are the two conditions satisfied by a subspace of a vector space. So we can say that in general we can say that a subspace of a vector space is a non-empty subset of the vector space which itself forms a vector space. Okay, so if closure under addition and closure under scalar multiplication can be satisfied, under the induced operations all the other properties of the vector space will clearly be satisfied. So subspace forms a vector space under the induced operations of vector addition and scalar multiplication in V. Let us see the first example. Determine whether the set S equal to set of all x, y, z belongs to R3 such that y equal to 0 is a subspace of R3 under standard matrix addition and scalar multiplication. So this S actually is a subset of R3. Clearly it is a subset of R3. Why? Because the elements of S are actually of the form x, 0, z. The second element must always be 0. Okay, so it is actually a subset of R3 under a restriction that the second element must always be 0. So if I am considering such a set, the question is whether that set is a subspace of R3. So we have to check. Two conditions. What is the first one? Okay, by the answer we can say that the given set is a subset. We are considering two elements U and V of S. So both the elements U and V will have its second entry 0. Okay. So U is A0B and V is C0D. So we have taken two arbitrary elements of S. Then we have to make sure that U plus V is in S. So what is U plus V? U plus V is equal to A plus C 0 B plus D. The second entry is again 0. So that is an element of S. So closure under addition is satisfied. What is the second condition? Closure under scalar multiplication. We know alpha dot U is going to be alpha A 0. Alpha into 0 is 0 itself. So 0 alpha V. That is again an element of S because the second entry is 0. So since the closure under addition and closure under scalar multiplication is satisfied, we can say that S is a subspace of R3. Let us see another example. Determine whether the set S is equal to set of all x, y, z belongs to R3 such that x equal to 3 is a subspace of R3 under standard matrix addition and scalar multiplication. So what is the peculiarity of the elements of S? The elements of S are of the form 3AB. That is, the first entry must always be equal to 3. Second and third entry can be anything. And will this be a subspace of R3? Let us check. So we have taken, as usual, we have taken two arbitrary elements of S. Anyway, the first entry will always be equal to 3. Then only that element will be an element of S. So we have considered U is equal to 3AB and V is equal to 3CD as arbitrary elements of S. Then what will U plus V be? U plus V will be 3 plus 3. The first entry will be 6. Then A plus C, B plus D. Will this be an element of S? No, because in order for an element to be a member of S, the first entry must be 3. But here the first entry is 6. So this does not belong to S. Hence, we can say that it does not satisfy the closure under addition property. So S is not a subspace of R3. Now let us see two important theorems on subspaces. The first one is, for any vector space V, a subset containing only the zero vector is a subspace. That is, for any vector space V, we know that every vector space will have a zero element which is denoted by the letter 0. This will be a subspace because the only entry here is 0. So 0 and under closure under addition, 0 plus 0 will be 0. So if I am naming this set as S, 0 plus 0 is equal to 0 belongs to S. And what is the second property? Alpha dot A. What is the only entry here? It is 0. Alpha dot 0 is equal to 0. Again belongs to S. So this S actually satisfies all the properties of a subspace. So the set containing only the zero vector will form a subspace for any vector space V. For any vector space V, there will always be two subspaces. We can say one is the zero subspace which contains only the zero vector. The other is the vector space V itself. Okay. So for every vector space there exist two subspaces. One is the zero subspace and the other is the vector space V itself. Also, in order to check whether a set is a subspace, we can have one thing. As we know that a subspace is itself a vector space. So a subspace must satisfy all the properties of the vector space. In particular, for a subspace to be, for a set to be a subspace, it must have a zero element, right? So if it does not have a zero element, from that moment itself we can say that it is not a subspace. So here in this example we can see that any element of this set is of the form 3ab. So the first entry will always be 3. What is a zero vector in S? In R3 it is 0, 0, 0. So 0, 0, 0, this vector does not belong to S. So from this itself we can say that this set is not a subspace of R3. Okay, so that is another method to check, to say that a set is not a subspace. But if there exists a zero vector, we cannot be sure that it is a subspace or not. Then we will have to check the properties of the subspace. Okay. Now what is the second theorem? A non-empty subset S of a vector space V is a subspace of V if and only if, whenever U and V are any two elements in S and alpha and beta are any two scalars, then alpha U plus beta B is also in S. That is actually a generalization of the two conditions, closure under addition and closure under scalar multiplication. Because suppose I am giving a restriction that alpha is equal to 1 and beta is equal to 1. What will this be? It will be U plus V. Sorry, this is not V, this must be V. Okay, so U plus V belongs to S agum. And the second one is, if I am giving the condition alpha equal to 1 and beta equal to 0, or if I am giving beta is equal to 0 here, what will happen? Alpha U plus 0, that is equal to alpha U belongs to S. So these two conditions are actually a particular case of this theorem. So in order to prove that a set is a subspace, it is enough to prove that for any two scalars alpha and beta and any two vectors U and V belongs to S, alpha U plus beta V belongs to S. Okay, this is another way of proving that a set is a subspace. Now there are 3 questions for you to work out. Which of the following are subspaces of R3? The first one is set of all ABC such that A is equal to B. So every element of this set will be of the form A, C. But the first and second entry is A. Will zero vector be a part of this set? Yes, because 0, 0, 0 has its first and second entry as the same. So this will belong to S. So from this we cannot conclude that it is a subspace. Only if it does not belong to S, we can clearly say that it is not a subspace. Now what about the second one? What is this? Here A must be equal to B plus 1. So here the entries are of a form B plus 1, B, C. So will 0 vector be a part of this? No, because suppose I am giving B equal to C equal to 0, the entry will only be 1, 0, 0. This entry, first entry will never be equal to 0 if the second entry is 0. Okay, so 0 vector does not belong to this set, and clearly we can say that this set is not a subspace. Okay, third one you can try to work out by yourself. So by this we can conclude the topic subspaces. We will see in the next class. Thank you.